Okay, I just wanted to go over a couple review problems here. So I would recommend pausing the video before we go through the solutions of each question and just trying it on your own. That being said, let's jump into problem one. A certain wave has a wavelength of 300 nanometers. What is the frequency of this wave? Well, there's two equations we're going to use for all of our wavelength wave problems in this class. And that's that the energy is equal to Planck's constant times the frequency, and that the speed of light is equal to the wavelength times the frequency. Conveniently, for wavelength, they use the Greek letter lambda, length lambda. And less conveniently, for frequency, they use the Greek letter nu. So, what equation do I want to use? Well, I don't know energy. I know Planck's constant, but I don't know the frequency, so that equation's out. But I do know the speed of light, I do know the wavelength, and I want to solve for the frequency, so that's the equation I'm going to use. Let's rearrange this to be the speed of light divided by wavelength is equal to the frequency. Okay, the speed of light is 3 times 10 to the 8 meters per second, and lambda, or wavelength, is 300 nanometers. And we want our frequency to come out in units of hertz, or per second. The problem here is that my units are in meters, and my wavelength units are in nanometers. This is not going to cancel out to leave just per second. So I need to convert one to the other. I would recommend always changing the speed of light into nanometers because it's going to be the same every time. Let's do that quickly over here. 3 times 10 to the 8 meters per second, but we just need to change the meters to nanometers because we're not changing the time interval. Well, I know that for every 1 meter, there's 10 to the 9 nanometers. And you may remember that when you multiply two numbers with the same base, you just add the exponents. So 8 plus 9 equals 17. So I'm going to say 3 times 10 to the 17 nanometers. And that's how far it travels every second. So I can come back over here and say 3 times 10 to the 17 nanometers per second. And that makes sense because now nanometers cancel out. I'm left with per second, and that's the unit I'm looking for frequency. You can type this into your calculator, or if you're taking the DAT or the MCAT, an exam where you don't get a calculator for questions like this, you can see that this is 3 times 10 to the 2 nanometers. Just like when we multiplied and we added the exponents together, when you divide, you subtract the difference of the exponents. So that 3 divides out, and 10 to the 17 divided by 10 to the 2 is 10 to the 15 hertz, which would be the frequency for this wave here. Great. How much energy in joules is in a wave with a wavelength of 575 nanometers? Feel free to pause the video if you want to. Let's look at what equations we have. Again, energy is equal to Planck's constant times frequency, or the speed of light is equal to, I should say, and the speed of light is equal to the wavelength times the frequency. Well, which equation do I want to use? It's asking for energy, so for sure at some point I need to use that equation. But I don't know frequency yet, so I'm going to have to solve for frequency here and plug it in there. So if I'm solving for frequency over here, I can say speed of light divided by wavelength is equal to frequency. That looks familiar from the last problem. And let's just plug this term in for frequency right there and say that energy is equal to Planck's constant times the speed of light divided by the wavelength. Now I just need to put my values into this equation and make sure the units work out. So energy is equal to Planck's constant, which is 6.626 times 10 to the negative 34. I said I always think of Lilo and Stitch there, agent 626, makes it easy to remember. And the units for Planck's constant are Joule seconds. Let's scoot over a little bit more, and we want to multiply it by speed of light over wavelength. Well, what's my speed of light? It's 3 times 10 to the 8 meters per second, or 3 times 10 to the 17 nanometers per second. I'm going to use that nanometer unit because I have nanometers on the bottom with a wavelength of 575 nanometers. Now I can see that nanometers cancels out and I'm left with seconds on bottom of a fraction sign, which will cancel out with that seconds there, and I just have joules as my unit of energy, and that makes sense. And when you run that through the calculator, you should get 3.46 times 10 to the negative 19 joules. A quick mental check we can do is if we have a wave in the visible light spectrum, so 575 nanometers is in the visible light spectrum, we would anticipate the energy of the wave to be somewhere around this 10 to the negative 19 joules. That's just a number that we might start to recognize as a value that makes sense for what we would predict the energy of this wave to be. So a quick mental check, if you get a number way outside of 10 to the negative 19, you get 10 to the positive 8 or something like that, you know that you're way off for a wave in the visible light spectrum. Okay, a common question that you might run into is asking you to compare different waves, but they give you different information about each one. So you're given wavelength or energy or wavelength again. Well, this problem is asking us which one has the greatest energy. So you might think, oh, let's convert these two equations into energy and compare, which you absolutely can do that. But I think it's a little bit faster to only have to change one equation. So let's change equation 2 here into wavelength, and then we can quickly compare all the wavelengths and know which has the greatest energy. So again, energy is equal to Planck's constant times frequency, and the speed of light is equal to the wavelength times the frequency. Well, I'm given wavelength, I know the speed of light, and I want to find energy. So I'm going to solve this very similarly to the last problem, where speed of light divided by the wavelength is equal to the frequency. And let's plug that in here. Oh wait, I'm trying to get from energy to wavelength, so it's not like the last problem. So I have energy, I want to solve for wavelength, so we're basically going to do the same thing but the other way, right? Where I'm going to solve for this frequency, knowing energy and knowing Planck's constant, and I'll plug it in over here. So I can see that energy divided by Planck's constant is equal to the frequency, and the speed of light divided by the frequency is equal to the wavelength, and that's the unit I'm looking for. Where that frequency gets plugged in there, so instead I can say the speed of light divided by energy divided by Planck's constant is equal to the wavelength. Hopefully that's clear to see. And so the speed of light is 3 times 10 to the 17 nanometers per second. I'm using nanometers here because I want my wavelength in nanometers because that's what the other two have. It would be harder to compare these nanometer lengths to a meter length that was some decimal, for me at least, because I don't use the metric system that often. So 3 times 10 to the 17 nanometers per second divided by my energy, which is given to us in the problem as 7.85 times 10 to the negative 19 joules. And I'm dividing that by Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. A quick once over of my units to see if they make sense. Joules got canceled there, seconds got canceled there. I'm left with nanometers, and that's what I'm looking for my wavelength. And it is equal to 268 nanometers. Okay, so that told us that this wave has a wavelength of 268 nanometers. The question wants to know which wave has the greatest energy. So I need to remember the relationship between wavelength and energy. I think it's easier if I can visualize two waves. This wave here with this long wavelength versus this one with this short wavelength. And to me, this wave just looks like it has less energy, right? It kind of goes do, 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 do. And this one goes, which is just a simple and silly way to quickly look at a wave. You just kind of let it speak to you, fill it out, and recognize that short wavelength means high energy. So who has the greatest energy? The other way of saying that is who has the shortest wavelength. Well, let's rank all these waves. The first one is the shortest, second one is a little bit longer, and the third one is by far the longest. So this wave is our answer here for the greatest energy. Okay, enough about waves. Let's talk about heat for just a second. These two problems here encompass pretty much everything we ran into in this class related to calculations of heat. So let's remember that our governing equation here is that energy is equal to the mass times the specific heat times the change in temperature. If we write this out with the units, joules is going to be equal to grams times specific heat times degrees. And just looking at that equation, it makes sense. Grams on top, grams on bottom, degrees on top, degrees on bottom, joules equals joules. That's true. So feel free to pause the video and solve this problem on your own. And let's do it. I'm cooking a steak with a mass of 400 grams. I first take it out of the freezer, which is this temperature, and place it in that much water to thaw. The water started at room temperature. Oh, I should change this. The water started at room temperature, which is 25 degrees C, and reached thermal equilibrium at 20.5 degrees Celsius. I hope nobody paused the video to solve it before I change that error. And so we reach thermal equilibrium at this temperature. What is the specific heat of the steak? Well, let's just kind of write down everything we know about the steak, and we'll use a different color to write down everything we know about the water. I don't know how much energy was involved with the steak, but I do know the mass is 400 grams. I don't know the specific heat. That's what I'm solving for. But I do know the change in temperature. It went from 0 and ended at 20.5. So that's a change of 20.5 degrees C. Okay, well, I can see right away I have two unknowns, the energy and the specific heat, and only one equal sign. So that's not going to work. Let's see if the water will tell us anything different. I don't know how much energy was related to the water or what happened, but I do know the mass because I was told I have 1.5 liters. I can convert that pretty quickly to milliliters by just moving that decimal over 3 places. And I know the density of water is 1 gram per milliliter, so I can say that that is 1,500 grams. Hopefully that's pretty quick to see. 1,500 grams of water, specific heat of water, we just have to know is 4.184 joules per gram degrees Celsius. And finally, the change in temperature, it went from 25 to 20.5. So that's a change of 4.5 degrees C. Technically, if you really care a lot, that's a negative change in temperature, right? Which would give us a negative energy as an answer, telling us that that's how much energy left the water, and all of that energy that left the water entered the steak. I don't really care about my signs too much because at the end of the problem, I'm just going to make sure whatever value I have, the sign makes sense for what I was asked in the question, and I might change it based off of that. So as I solve through these, I never really care too much about my sign. But if you're somebody that cares, that's negative, and the negative energy of the water, or basically the energy loss of the water, is equal to the energy gain of the steak. So because of what I just said, the energy loss and gain are equal, you could just say this term is equal to this term. And if you're really caring a lot, it's technically like the negative version of that term, right? And this is how I've typically seen it written out in books or like online. But just to make it really clear what we're doing, and obviously you would solve then for this equation here, or for that variable. To make it really clear, let's just solve for the energy loss of the water. So I multiply all these things out together, and I get 2, 8, 2, 4, 2. I'll just say one last time, again, if you've been caring about your sign, this is negative because that's how much energy was lost, but I don't care about the sign, and I'm not going to talk about it anymore. So that's our energy of the water. and it all went into the steak. So now I can plug that in. The energy of the steak, the energy it gained as it thawed was 28242 joules, and that's equal here to 400 grams times my unknown specific heat times my change in temp. Just kind of scoot this over. Okay, well, if I want to isolate this variable, I need to take this one and move them over here, right? Divide by both of those. So 28242 joules divided by 400 grams, also divided by 20.5 degrees Celsius. And I'm trying to solve for specific heat. Well, my units tell me that I've done a good job because I have joules on top, grams per degree Celsius on bottom, and that's what I have over here. So the units all match up, and when you run that through your calculator, you should get 3.44 joules for every gram degree Celsius. And this is where I just check my sign. Does that make sense? It does make sense. Specific heats are usually reported as positive values. If you got a little confused with your signs along the way and ended up with a negative 3.44, then that's still true, right? It's just telling you that you have to take out 3.44 joules of energy every time you want to lower the temperature of the steak, 1 gram of the steak by 1 degree. Okay. So use the information from the previous question, or using that information, how many milliliters of propane do I need to cook this steak from 20.5 degrees C to a nice medium rare at 55 degrees C? It also gives me the density of propane here. Okay, well now we know the specific heat, so we can solve some things about the energy required to cook this steak, right? It's 400 grams. I don't know if when you thaw steak it gets heavier from being in the water, but let's just say it's 400 grams. We now know the specific heat was 3.44 joules per gram degree Celsius. And the change in temperature, it's no longer what it was, right? It used to be 20.5, but now it is 55 minus 20.5, right? Where we ended subtracting where we started. That's how we find the change. Run that through your calculator, and the energy required to heat the steak is, let's see, 47472 joules required to cook the steak. But my question wants to know how many milliliters of propane. Okay, that might seem really abstract and confusing of how am I going to get from joules of energy to milliliters of propane? But it's all given to us in the problem. If we take joules to kilojoules, then we can use this conversion factor where we know how much energy was released by 1 mole of this reaction, which is 1 mole, uses 1 mole of propane. So we can get from kilojoules to moles of propane. Using the molar mass, we can get from moles of propane to grams of propane, and using this conversion factor, we'll find the milliliters. So let's do exactly that. To find the kilojoules, I just count in 3 decimal places, right? So 47.472 is my kilojoules of energy. We'll write it right there just so the conversion factors are really easy to see. And now, following that path I just described, let's get kilojoules of energy into milliliters of propane. So using this here, I know how many moles, I'm just going to write a capital P for propane, there were related to the energy. And then I can go from moles of propane to grams of propane because I can figure out the molar mass. And then grams of propane to milliliters of propane. There's no way I could have figured that out, but it gave me the density, so I can do it. And that's where I want to go, right, is to milliliters of propane. Do my units make sense? Kilojoules are gone, moles of propane's gone, grams of propane is gone, and I'm left with the unit I want for my answer. So now all I have to do is make sure I add the right numbers. Here's my conversion factor for energy to moles. Let me just scoot that unit over. 2220 for every 1 mole. I know I said I'd stop talking about sign, but you might think, oh, but it's negative energy. Okay, you could say that. You would get negative energy at the end and you'd have negative milliliters. I guess that's just a way of describing how many milliliters of propane you lost in the process, so that still all makes sense. But I'm specifically talking about the energy that went into the steak, and so it's still a positive value. But like I've said before, I really don't care until I get to the end, and I'll just make sure my sign makes sense. Okay, moles of propane to grams of propane. You can just add this together. Here's 3 12s and 8 1s. It comes out to be, if you get more precise than that, 44.1 grams for every 1 mole of propane. And then I'm given the density, 1 milliliter of propane has a mass of 0.0015 grams. You run that through the calculator and get 629 milliliters of propane. Does that make sense for my question, that sign? How many milliliters of propane do I need? You need 629. If somebody asked you how many milliliters of propane do I need, and you said negative 629, that wouldn't make sense. And if I was writing the test, I would mark you wrong for that because it's silly. So positive 629 milliliters of propane. Hopefully that was helpful. You can reach out to me if you have any questions, and thanks for watching.